Hello Math 1090 team. Today I'd like to start looking at sections 6.2 and 6.3, savings annuities and payout annuities. For most of us, we aren't able to put a large sum of the money in the bank today for retirement. Instead, we save for the future by depositing smaller amounts of money from each paycheck into the bank. This idea is called a savings annuity. Most retirement plans like 401k plans or IRA plans are examples of savings annuities. So let's get started. Let's look at some definitions that we can use first. A savings annuity is an account that's funded by regular deposits, usually monthly, into an account. Now, the formula for a savings annuity looks like this. In our savings annuity formula, A is your balance after T years, the left-hand side. D is your regular deposit amount, times 1 plus R over K, where again, R is your annual interest rate written as a decimal, and K is the number of compounding periods per year, raised to the KT, where T is time in years, minus 1 divided by R over K. Now, I'm not going to have or require you to memorize this formula. I will provide it for you on our future exams and the final. It's your responsibility, though, to know when to use this formula when you're talking about a savings plan and how to use the formula. Let's look at an example to get familiar with this. Suppose you decide to invest $225 every month into an account that earns 6.4% APR for 30 years, compounded monthly. Okay, part A. How much will be in the account? So the account balance. Let's start with our savings annuity formula. A, this is the amount in your account. It's going to be equal to D. Remember, D is the amount that you deposit each month. We deposit $225 each month. Times a bracket. 1 plus your interest rate R, written as a decimal. So ours was 6.4%. So 0.064. Divided by K, which is going to be the number of times you compound per year. We're compounding monthly, so divided by 12. Raised to the KT, so 12, where T is our time in years. We're depositing money for 30 years, minus 1. All divided by, again, your interest rate divided by your number of compoundings. So 0.064 divided by 12. Now I'm going to use my calculator to help me calculate this. Now everyone's calculator is differently, but to be clear, sometimes we need to use parentheses as grouping symbols for the numerator or the denominator. And so you might want to get in the practice of grouping your numerator and denominator together with parentheses. This one already has a pair of parentheses, so I won't duplicate it. Okay, so let's use our calculator. This is going to be grouping symbol, numerator, 225 times, this parenthesis recognizes or is for this bracket I wrote here. Then another parenthesis that represents this parenthesis in front of the 1. So this is going to be 1 plus 0.064 divided by 12. Now I need a parenthesis that ends this one after the 12. raised to this exponent, which I use the caret key. Now, everyone's calculator is differently. My calculator clearly shows me the exponent is an exponent. However, if yours does not, you may also need a pair of parentheses here to group your exponent. And then a parenthesis to close off the exponent. Then I have the -1. Notice the -1 is not in the exponent, so I'm going to arrow over to get it out of the exponent and do -1. And then another parenthesis. This parenthesis signifies this bracket I have right here in blue. And then one more parenthesis. That parenthesis signifies this red parenthesis that I used to group the numerator. Divided by 0.064 divided by 12. Okay. Now if I did this correctly, I have the account has a balance of $244,107, and if I round this to the nearest penny, 31 cents will be the value of our annuity after 30 years when you make regular contributions of $225 every month. Now part B, how much did you actually deposit? Now this is the value of the account, but that's not the same thing as the amount of money that we deposited. Now I don't have a formula for this, but we can think our way through it. The amount deposited. Well, we're depositing $225 every month, and we do that for every month out of the year for 12 months. This represents the amount of money deposited for 1 year. But we're doing it for 30 years, so times 30. So 225 times 12 times 30. And I get $81,000. Now what we should notice right here is that even though we deposited every month for 12 months a year for 30 years, we only deposited $81,000, but the account actually has $244,000 in it. The difference of this is the interest the account grew by funding this for 30 years. How much interest did we actually get? Well, that's part C. So here our interest. Let's put interest gained. Well, we had in the account the $244,107.31 minus the $81,000 that we actually deposited. And I get $163,107.31. This is all money that we benefited from because of interest that the account gained over that 30-year period. Okay, let's look at another example. Suppose you want to retire in 25 years and you want to have $500,000 in your account. You found an annuity that pays 7.5%. Now the question, what amount will you have to deposit each month to accumulate to that $500,000? So notice in this question, they're asking how much do we need to deposit each month? Let's start with our annuity formula. So here we have A equals, again, it's your monthly contribution D times 1 plus R over K. You'll need parentheses around that. Raised to the KT minus 1, all divided by R over K. Now, there's different ways to do this problem. Some students like plugging in the numbers for R and K right now. However, I'd like to approach this problem a little differently because I know we solved this problem a lot in our homework. So rather than plugging the numbers in, I'm going to solve for the variable D that we're interested in, but I'm going to do it while I leave everything in terms of variables. So let's see how this goes. If I'm going to solve this expression for D, I want to get D by itself. Maybe the first thing I would do is multiply both sides of this equation by R over K. This will do the job of canceling this R over K on the right-hand side, leaving us with the expression A times R over K equals D times the parenthesis 1 plus R over K raised to the KT minus 1. Now, I'd like to get D by itself. So to get D by itself, let's divide both sides by this bracketed expression. So we'll divide both sides by 1 plus R over K raised to the KT minus 1. And also divide the left-hand side. And this will do the job of allowing this right-hand side to cancel these bracketed expressions. And what I get back is an expression just for D. Now D is going to be this A times R over K divided by the bracketed expression 1 plus the R over K raised to the KT minus 1. Now in your homework, you're going to have to solve for D several times, and I think by seeing it without the numbers in it, you'll recognize the pattern. Okay, now let's plug in all the values we have for our variables. The A, that's the $500,000 that we want to have. Times the R divided by K. Again, your R has to be an interest rate as a decimal. So 0.075 divided by 12. All divided by 1 plus your interest rate. Oh, and write the interest rate as a decimal. So 0.075 divided by 12 raised to the 12 times. This is going to be the amount of time that our investment is there for, which is 25 years, minus 1. Now I'm going to grab my calculator to input this. But again, depending on your calculator, you might have to use more parentheses. I'm going to put a grouping symbol around the numerator just to make sure my calculator sees this as a numerator. On the denominator, we already have the brackets. I don't need to put another one. So calculator. Let's put our grouping symbol to start the parenthesis. The 500,000 times the 0.075 divided by 12. The first parenthesis there closes off the one that started my interest rate. Another parenthesis will close off the numerator, where I put this parenthesis in front of the 5,000. Divided by a parenthesis. Now I'm using this parenthesis to represent the bracket since my calculator does not function with brackets well. Then a second parenthesis, 1 plus 0.075 divided by 12. And a first parenthesis here to represent this one that's after the 12. Raised to the exponent. I use the caret key for my calculator. Yours might be a little different. Now, depending on your calculator, you may have to also put grouping symbols around your exponent so your calculator knows that this is an exponent. You may need parentheses here. Now, my calculator doesn't because it clearly shows this as an exponent, but just for the practice, let's put the parenthesis 12 times 25, parenthesis. Now I have to go minus 1, and notice the minus 1 is not in the exponent, but my cursor is, so I'll arrow over to get out of the exponent and put the minus 1, and then put that parenthesis to close off the bracket that was representing my denominator. Okay, I hope you can confirm this, but what I get out of this is, let me do this in the same color so it all matches. So what I get out of this is a monthly deposit amount of $569, and if I round this to the nearest penny, 96 cents. So remember what this represents. It was asking us, how much money do you have to deposit each month so that after 25 years, you have $500,000? And this tells us we have to deposit $569 every month to accumulate to that balance. Okay, now part B. So this was all part A. Part B. How much interest will we earn? Now, in the last problem, I broke this up as 2 steps, but here I just wrote it as 1. To figure out how much interest you earn, you first have to figure out how much you deposit. So your deposit amount. So remember, you're depositing $569.96 every month. And you're doing that for 12 months a year. And you're doing that for 25 years. So at the end of that 25 years, you would have deposited $170,988. This is the amount that you would have deposited. But remember, you have $500,000 in there. So how much interest did you earn? Well, your interest, that's going to be the amount of money that you actually claimed as you funded this annuity. It'd be the $500,000 minus the $170,988. Which comes to $329,012 of interest that you get to claim. Now, I think this is very impressive and worth taking a moment to think about. We deposited $569 every month for 25 years, and at the end, we deposited a total of $170,988. And this may not be enough for you to retire on. But because of the benefited interest we got to claim, the $329,000, we now have $500,000 in our retirement account. And this may be enough for you to retire on. I guess it really depends on your spending habits. Okay, let's look at another example. Suppose you have a friend that wants to retire at the same time as you, but they waited 10 years before starting their savings annuity, so now they only have 15 years left. Their annuity also pays 7.5%. And now the question, what amount will they have to deposit each month to accumulate to that $500,000 like you had? So notice this question is asking, how much do they have to deposit? Okay, let's get started. Our starting place again is your savings annuity formula. A equals D, your monthly contribution amount, times parenthesis 1 plus R over K raised to the KT minus 1 divided by R over K. And again, I want to solve this formula for D. But I want to do it a little bit faster than we did last time. So to remind ourselves how we did it, let's look back. To solve for D last time, what we did is we multiplied by the R over K to get it on the left-hand side next to the A. And then we divided by this bracketed expression to write it in the denominator. And that's how we got D by itself. Now I could just use the formula we've already solved, but again, I say in your homework you're going to do this several times, so I'd like to reiterate this method. But this time let's do it with less steps. If you're going to solve for D, the first thing you're going to have to do is multiply it to get the R over K onto this left-hand side. And then you're going to divide by this bracketed expression. So D. If you multiply to get the R over K on the left, you'll have A times the R over K. Then you're going to have to divide by this bracketed expression to get D by itself. So now I'll divide 1 plus R over K raised to the KT minus 1. Okay. Now let's plug all the values that we have. D. Well, that's going to be the amount that you have in the account at the end, which is going to be that $500,000. Times your interest rate divided by the number of times you compound interest. So remember where our interest rate was the 0.075 divided by 12 because we compound monthly, divided by 1 plus the 0.075 divided by 12 raised to the KT, which is going to be 12 times T. Now be cautious here. Remember, T is the amount of time that they are saving, that they're funding this annuity. And because your friend waited that 10 years, they only have 15 years left. So times 15 minus 1. Okay, and let's enter this in our calculator. Again, depending on your calculator, you may want to use more grouping symbols. So you may end up putting a pair of parentheses around this numerator just to make sure your calculator knows that's a numerator. I don't have to do it on the denominator because these brackets already do that. So here we go. 500,000 times the 0.075 divided by 12. The first parenthesis there closes off the one where I started the interest rate, and then another parenthesis to close off the numerator, the top of the fraction. Divided by a first parenthesis that represents my bracket, and then I need another parenthesis. So it'll be 1 plus 0.075 divided by 12. Now I need a parenthesis to close off my interest rate. Raised to the exponent. And again, depending on your calculator, you may need to put parentheses here. 12 times 15. Minus 1, but again, notice the minus 1 is not in the exponent, so I'm going to arrow over to get out of the exponent and do the minus 1. And now I need a parenthesis that represents this bracket to close off the denominator. And I get a deposit amount that's $1,510. And if I round that to the nearest penny, 6 cents. Now let's take a moment to compare to our last example. In our last example, you were going to save for 25 years. And for 25 years, if you want to get $500,000, you ended up having to save or deposit $569 every month. However, because your friend waited to start their retirement account, they now have to deposit $1,510 every month. This is considerably more. And the reason is, well, they didn't have that 10 years of time to benefit from. Because they waited 10 years, they obviously have to deposit more. Okay, let's explore this just a little bit more. Now, although the question doesn't ask it, let's look at how much is actually deposited. Okay, well, they deposited $1,510.06. They did this for every month, 12 months out of the year, and they're doing this for 15 years. So 1,510 and 6 cents. Let's not introduce too much rounding error. And we did this for 12 months out of the year for 15 years. So your friend is going to end up depositing $271,810.80. Remember, in comparison, you only had to deposit $170,000. Your friend now has to deposit $271,000. So pretty much $100,000 more they will deposit. Now they're still going to have $500,000. They just have to deposit considerably more to accrue to that amount. The last question I could look at, or last comparison, I could look at the interest. So here the interest earned is going to be the 500,000 minus the 271,810.80, which comes out to be $228,189.20. So they still get to claim considerable amounts of interest here. But in comparison, they got to benefit from $228,000 of interest, while you got to benefit from $329,000 of interest. And this, again, this is due to the fact that they waited 10 years to start this. Now, I think the bigger thing to walk away from these two examples is to ask or answer the question, when should you start your retirement annuity? And the answer is as soon as possible. Waiting 10 years means that you had to deposit significantly more money, $569 versus $1510, and you got to benefit from significantly less interest, the $329 versus the $228,000. So the point is, when should you start your retirement account? As soon as possible. Okay, let's look at another example. Mr. Smith has decided to invest $270 each month in an account that pays 7.9% interest, compounded monthly. After how many months will the account be worth $63,000? So this question is asking us to find time. More specifically, how much time for the account to grow to $63,000? Okay, so let's start with our savings annuity formula. A is going to be your regular deposit amount, your 1 plus your interest rate divided by K, raised to the KT minus 1, divided by the R over K. And let's start by plugging all the values in for our formula. So this will be A, your account balance. Now remember, you're making $270 contributions. 1 plus your interest rate written as a decimal, so 0.079 divided by 12, raised to the 12t, where we don't yet know what t is. That's the question we're trying to look at, how much time, minus 1, all divided by the 0.079 divided by 12. So remember, this is the formula that tells you how much you're going to have in your account at any time. Now, our question is asking, when will this reach 63,000? So we're trying to solve this formula, or solve this equation. We're trying to find out, when will this reach 63,000? Okay, so here we go. Let's solve this for when this equals 63,000. Let's figure out, what does t have to be? So to start with, you probably want to get rid of your fractions. So maybe you could multiply both sides by the 0.079 divided by 12. This will do the job of canceling this fraction on the left-hand side. And I think what we get back is going to be the $270 1 plus the 0.079 divided by 12, raised to the 12t minus 1. And maybe to help us, I'm going to go ahead and multiply this right-hand side out. 63,000 times the 0.079 divided by 12. Parenthesis. And I get 414.75. Now, this came out to be a pretty nice number. If it were not so nice, you'd probably want to consider how many digits you'd like to carry in your decimal to avoid rounding errors. But this one was pretty nice. Okay, now let's continue to solve this for d, or sorry, for time t. And so let's divide both sides by the 270. So I think this will give us the 1 plus the 0.079 divided by 12 raised to the 12t minus 1 equals, now the right hand side, the 414.75 divided by the 270. And I'm going to keep significant numbers of decimals here just to avoid rounding error. I'm going to write 1.536, and I'm going to go to 5 decimal places. 1, 1. Okay. Now to, again, keep going with this, we want to solve for t. So maybe to get rid of this minus 1, we can add 1 to both sides. So now we'll have the 1 plus 0.079 divided by 12 raised to the 12t equals, when I add 1, I think it'll be 2.53611. Okay, now using the work that we did from back in chapter 5, I want to get this t out of the exponent. So this is where we choose to apply a logarithm to both sides. And I like using the natural log. And this allows us to use the property that natural logarithms can bring exponents as coefficients. Oh, I jumped around. We get back to where we were at. Okay. So if I bring that exponent as a coefficient, we now have 12t natural log 1 plus the 0.079 divided by 12 natural log of the 2.53611. And now to solve for t, let's divide both sides by the thing that's not t. And this will allow us to say that on the left-hand side, everything that's not t will cancel. And so t will be equal to the natural log of 2.53611 divided by the 12 natural log of 1 plus the 0.079 divided by 12. And again, to be explicit, your calculator is probably going to require that you put a grouping symbol on the denominator to interpret this denominator correctly. So let's see what we get. So we have the natural log of 2.5611 divided by a parenthesis for my denominator. This would be 12 times the natural log of 1 plus 0.079 divided by 12. One parenthesis to close off this blue one that I have for the natural log, and another parenthesis to close off my denominator for the fraction. And I get approximately 11.9 years. Now, the way to interpret this again is, remember, we're asking how much time for the account to grow to $63,000? Well, if we invest $270 each month at 7.9% compounded monthly, it'll take 11.9 years for the account to grow to the $63,000. Okay, I'm going to stop this video here. I've made it through the first 7 pages of our guided notes so far. However, since the video is already at 41 minutes, I'm going to stop here and look at the next couple of pages for payout annuities in another video. I will see you there.